In our last lecture, if you recall, within our discussion on TCP IP, we had looked at some of the fields of the IP header which are responsible for the fragmentation and reassembly of packets, and finally we looked at well, some issues regarding IP addressing, the address classes. In this lecture, we shall be discussing the transport level protocols that exist in TCP IP. So, today we would be primarily looking at some of the features of the two transport level protocols in TCP IP, namely the transmission control protocol TCP and the user datagram protocol UDP. Now, these being transport layer protocols, the basic idea is that the applications which are running on the end hosts, which you can treat as processes, as programs in execution, they will be interacting with the TCP IP protocol suite by sending or receiving either TCP or UDP data, depending on which of these protocols the application chooses to use. But one thing to note is that both TCP and UDP, they sit on top of the IP protocol. So, both TCP and UDP will be generating the packets and forwarding them to IP for delivering them to the correct destination. Pictorially, the hierarchy looks like this. Let us have another look at this diagram. So, here in today's lecture, we will be concentrating on this part of the hierarchy, the transport layer protocols TCP and UDP, where the user processes will be sitting on top of them and the IP protocol would be sitting below them. Okay. So, this is where TCP and UDP exists in the protocol hierarchy. Now, first let us look at what are the basic purposes and roles of the TCP protocol, the transmission control protocol. Now, one thing to note is that the main difference between TCP and UDP is primarily related to the kind of service that it provides to the applications which are invoking them. Okay. So, TCP provides a so called connection oriented, reliable, full duplex means bidirectional and byte stream service. This means that the two end hosts will have to establish a connection before data communication can start. Communication is reliable. Reliable meaning even in case of some failure or some packet loss, TCP will try to recover from that failure and regenerate the packet, retransmit it if necessary. Full duplex means bidirectional, and byte stream means to the applications the messages which are sent and which are received as if they are a stream of bytes. But the point to note is that the underlying IP layer which TCP uses for the actual transport of the data is unreliable, and also it is a datagram service, which means it is connectionless. There is no concept of connection establishment in the IP layer. So, the question is that how then TCP ensures that the connection is reliable, the communication is reliable, and there is a connection oriented service. It does so by explicitly maintaining a few things. First, a checksum to check whether a packet or whether a TCP message is correct or not, positive acknowledgements to send back information to the sender that well, all the data messages have been received correctly or some have not been received, timeouts, if acknowledgements do not come within a certain time, then the data is again sent, is retransmitted, and flow control. Flow control means if the sender is sending data too fast, the receiver cannot accept it at that rate, the receiver can send a request to the sender that well, you please slow down the speed of transfer. Okay. This is called flow control. TCP in addition, since it is a connection oriented service, it also handles establishment and termination of connections between applications or processes and sequencing of data. Sequencing means at the level of TCP, say I am trying to send a message, it can be broken up into several packets and they may be sent by IP. Now, IP does not guarantee any sequencing, the packets may reach the destination in any arbitrary order. So, what the TCP layer at the receiving side must ensure is that all those small pieces that constitute the original message must be put together in the original order before they are forwarded to the application. So, application will have a feeling that the message is coming in sequence in the order of bytes, in byte order. They will not be forwarded to the application in an out of order fashion. Okay? Fine. Now, in contrast, the user datagram protocol or UDP, it provides a connectionless and unreliable datagram service. So, in this sense, UDP is very similar to IP, because IP is also connectionless, IP is also a datagram based service. So, now the question is that if they are so similar, what extra does UDP have over IP? Well, in fact, UDP provides two additional things in addition to what is being provided by IP. The first feature is a checksum which can be used to verify the integrity of the UDP packet. Of course, this checksum is an optional field. If it is not used, the checksum field is set to all zeros. Secondly, and more important, is that it keeps track of something called port numbers. These port numbers will identify the processes at the two ends, because when UDP sends a packet to a destination, it is targeted towards a particular process or an application which is running at the destination. So, the port number in the packet will uniquely identify that which destination this packet must go to. So, if the port number was not there, then all packets which are targeted towards all applications running on a particular machine would reach that machine, and there would be no way to find out which packet should be sent to which application. Okay. So, port number is used specifically for that purpose. So, this is exactly what I just talked about. Multiple user processes on a machine may be using the transport layer protocols TCP or UDP at the same time. So, when data packets are received, they are coming to the machine, there is a need for a mechanism so as to uniquely identify that which process the data packets need to be forwarded to. Let us look at this diagram to illustrate. Suppose this box indicates a host on the internet. This is a computer, and inside this host there are three processes, process 1, process 2 and process 3, which are executing or running. Suppose we assign port numbers 10, 20 and 30 respectively to these processes. So, when an incoming packet is coming to this host, it must also carry along with it the port number. So, if it carries a port number of 20, then the packet will automatically be delivered to process 2. If it carries port number 30, it will be delivered to process 3 and so on. So, this simple illustration will help you understand the importance or the need for having these port numbers. Port numbers will uniquely identify the applications which are running on the hosts. Now, port numbers are 16-bit quantities. They are used to address an application, and you recall IP address is a 32-bit quantity which identifies a host. In contrast, the port number is a 16-bit quantity. So, both TCP and UDP uses these 16-bit integers to represent port numbers, and as I have mentioned that applications are uniquely identified by different values of the port numbers, and the TCP or UDP packets will have the port numbers stored in their headers, so that the packets can be delivered to the correct application. Okay. So, just another look at this picture. In this hierarchy at the lowest level Ethernet, here we address with respect to the Ethernet address, which is 48 bits. At the level of IP, we use the internet address or the IP address 32 bits. At the transport layer level, we use port address to identify the application, and this is 16 bits. So, at the different levels of this hierarchy, we use different ways of addressing the entities. At the lowest level, we are identifying the physical interface. At the next higher level, we are identifying a host. At the next higher level, we are identifying a particular application which is running on the host. Okay. Now, in a typical client server scenario, let us see what happens, because this client server scenario is so common nowadays. There is a server program which is running on some machine and is providing some service to other so called client programs, and a client program running on another machine can send an explicit request to the server. The server program will be receiving the request, will do the needful and will be sending back the response to the client. So, this is how the client server environment works. Now, let us see. In the client server scenario, by knowing the 32-bit IP address of the server, a client host can first establish a connection to the server. But not only this, in the client server scenario, the appropriate server program, the particular process must also be identified. So, the client must also know the corresponding port number. This means that whenever you are working on the client server scenario and a client wants to connect to a server, you need to know the IP address of the server machine and also the port number which will identify the particular process which is running on the server machine. Say for example, you just think of the World Wide Web, the so called HTTP protocol. Now, whenever you are using a browser, you are wanting to visit a site, you first type in either a site name or an IP address. There is a mechanism to translate a name into an address that we will be talking about later, but in some way it is getting translated into an IP address. But in addition, in your browser setting, somewhere it is said that if it is an HTTP request, by default set the port number to 80, because 80 is a number that identifies the HTTP server which runs on the other machine. So, in this way both the IP address and the port numbers are specified by the client. Okay, fine. Now, among the port numbers, there are a set of such port numbers which are predefined and are made publicly available or publicly known. For example, port number 21 is used for the file transfer protocol, for transferring files between machines. Port number 25 is used for the simple mail transfer protocol which is used in emails. So, these are just two examples. There is a big such list which can tell you the list of all publicly available port numbers which everyone can use in order to contact a server on some particular machine. Now, information regarding these port numbers and these servers are stored in computer systems in a particular directory, because a computer must also know in some way that well port number 21 corresponds to the FTP protocol and port number 25 corresponds to the SMTP protocol. There is a particular file somewhere in the machine which contains all these details. These so called well known port numbers are stored in a file which on a Unix machine, this is stored in a directory under root etc services. And another example, under the Windows XP environment, it is stored in a directory like this, under C Windows System32 drivers etc. In this file there are a set of lines or records. Now each line or record has the format. So it starts with the service name, then the port number, then the protocol, then the aliases, that means I can have some other names to the service names, followed by the comments. I will show an example in the next slide. Few lines of such a file we shall be having a look now. Yes, this is the contents of the first few lines of the etc services files in an Unix machine. The first column, these identify the names of the services or the servers. You see here you have somewhere FTP, you have somewhere SMTP, and there are others also, echo, systat, etc. Now you look at the other fields. FTP, it says here 21/TCP. This means FTP protocol uses port number 21 and the TCP protocol. This is a comment line, just it says that it is an FTP protocol. This is a control connection. Take some other example, say SMTP. First it says port number 25 TCP protocol. There is an alternate name or alias, this is called mail. So instead of SMTP you can also refer to this service or server as mail mail. Okay. Now you can see here some of the protocols also use the UDP protocol, port number 7 UDP. So this is the kind of information that gets stored somewhere in each computer system, so that when a particular packet comes, just by looking at that file the operating system can decide to which program the particular packet should be forwarded to, because the information about port number and also the protocol TCP or UDP, that is stored there. Okay, fine. Now there is something called ephemeral port numbers. Let us try to understand what this is. Well, let us look at a typical scenario. A client process sends a message to a server which is located on some host, say at port number 1534. Now the server will have to respond back to the client. The question is, how will the server know where to respond, because the server does not know the port number of the client process, and the server is well known, the client is not well known. Okay. So what the client process will do, the client process will request the local operating system for an unused port number. It gets generated. Okay. These unused and temporary port numbers are called ephemeral port numbers. These are purely temporary. These temporary port numbers exist only for the duration of the current connection. After the connection is terminated, the port numbers are withdrawn. So these are purely temporary port numbers used on the client side. These are called ephemeral port numbers. Now with respect to the port number assignment, well, typically the port numbers starting from 1 up to 1023, these were reserved for well known port numbers, but some of the applications today also extend this number up to 4095, but anything beyond this up to a maximum of 65535, this can be used by a client program as ephemeral port numbers. So you have a pretty large range of port numbers available for use on the client side, and these numbers are used as the ephemeral port numbers whenever the client wants to make a connection with the server. Okay. Now talking about connection establishment, there is a hierarchical addressing scheme. There are three things which need to be specified when you establish a connection. First is the IP address of the two ends, the source and the destination. Next is the protocol, whether you are using TCP, UDP or any other protocol. The third is port number to identify the processes at the two ends. Okay. These are the three things you need to specify when establishing a connection. Now, when a connection is established, we define something called an association. Now, association is actually a collection of these 5 things: the protocol, TCP or UDP, local IP address, local port number, remote IP address, remote port number. The example of association is this: this is TCP address, local IP, local port, remote IP, remote port. These will be dots. Okay, fine. So, this example, these 5, so means information, these 5 components of this association will be able to uniquely identify a connection which is getting established. Okay. So, when you say that a connection has been established, it means both the sides have come to know all the 5 components of an association. Only then the packets can be sent and received with all the relevant information. Okay. So, now let us have a quick look at the format of a TCP packet, the TCP header, how TCP carries out encapsulation. This is the diagram that shows a TCP header, a TCP segment which contains source port, destination port, sequence number, acknowledgement. There is a header length, flags, there are some reserved fields, window, checksum, urgent pointer, and again there are some optional fields here. Now, let us very quickly see that what these fields are used for. Okay. Fine. Source port and destination port numbers are self explanatory. Sequence number is used for reliable communication. Now, you are trying to transmit a message. Now, a message may not be transmitted in one go, it may have to be broken up into smaller pieces, and several TCP packets may be generated corresponding to the same message. So, what TCP will do? TCP will assign a sequence number to each piece of the message, and that sequence number will correspond to the starting byte number in the original message from where that piece starts. Okay. So, each byte of message is assigned a 32-bit number. This is a byte level addressing, that is incremented sequentially. The field holds the number of the first byte of that particular TCP segment you are trying to send. Similarly, from the other side, you have an acknowledgement number 32-bit which is sent back. The remote host is using this to acknowledge something. This contains the number of the next byte expected to be received. This means if the sender has if the sender is sending the TCP segments one after the other, the receiver has received the packets say up to byte number 1000. So, receiver will be sending back an acknowledgement with acknowledgement field value as 1001. So, it says that 1001 is the next byte I am expecting. So, these acknowledgements help TCP in knowing, or the sender to know, that whether receiver has received all the segments correctly or not, and if not, the segment which has not been received correctly is transmitted again. So, even in case of failure, the failure is overcome through retransmission. Okay. Then just like the IP protocol, we have a header length field 4 bits. This also specifies the header length in terms of 32-bit words. Okay. Flags, there are 6 flags and their purposes are various, but I am not going to detail. I am just mentioning some of the typical uses of these flags. There is a urgent flag URG. This is set to 1 if the so called urgent pointer is in use. Well, urgent pointer actually points to some segment in the data which can contain some very important information for the receiver. So, if the urgent pointer is set to 1, the receiver can immediately take out that urgent data and process it immediately. And there is a SYN flag and an ACK flag. if it is 1, SYN is 1 and ACK is 0, this means the sender is trying to send a connection request. If both are 1, it means the connection is confirmed. There are other combinations also, and fin is another flag, finish. When the sender has no more data, fin equal to 1 is sent to release the connection. That means now the connection can be terminated. There is a reset bit, RST. This is used to reset or to reject a connection request. There is a push flag. This is used typically to indicate end of message. And there is another very interesting field, window field is a 16-bit window field. Actually, TCP uses a kind of sliding window protocol at the level of bytes, and the window field indicates the current size of the window. Say if the window field contains a value 5000, this means that the sender can transmit maximum up to 5000 bytes without an acknowledgement coming back. Okay. So, it specifies how many bytes may be sent beyond the byte acknowledgement. This number is called window advertisement. Now, this number can be increased or decreased as per the requirements. Suppose the receiver finds that the sender is transmitting data too fast, it is not able to receive it at that rate. So, now what the receiver will do, it will send back a TCP request to the sender requesting it to reduce the value of the window. So, if the window value is reduced, then the sender is prevented from sending data at that rate. So, the rate can be increased or decreased by appropriately setting the value of the window field. So, if the value of this window field is set to 0, this means the window will be closed altogether. That means the data transmission will stop. Now, this window field is actually used for congestion control in the network. If a segment of the network becomes congested, congested means the speed goes down, the buffer space gets filled up, then the window size may be reduced through a proper negotiation protocol, so that the congestion can be reduced. So, this congestion and flow control, these are two things which are served by this window field in TCP. And lastly, there is a checksum field which is 16 bits. Now, the way it is computed is the same as IP, that means the algorithm use the same as IP. You take 16-bit segments of the numbers, you take a ones complement sum and finally take the ones complement of the result, that is the checksum. But the data on which this algorithm is applied, there is something to observe here. This checksum applies to the entire TCP segment plus a pseudo header. Pseudo header contains some information which are borrowed from the IP headers. Pseudo header contains the following fields: source IP address, destination IP address, protocol TCP or UDP, and the segment length. Now, the purpose of including this pseudo header in this checksum computation is that, suppose say IP is an unreliable service, TCP knows that. Suppose by mistake IP forwards the packet to a wrong destination host. So, there at the final destination, when this TCP checksum is computed, that error will be found out because the IP addresses are different. Okay. So, this feature of pseudo header is mainly used for protecting TCP from misdelivery by IP. So, some of the failures of delivering a packet to the correct destination by IP is taken care of by using this pseudo header. Okay. Now, let us look at the UDP protocol, UDP header format. Now, as you can see from this diagram, the UDP packet structure is extremely simple. there is no fancy headers, only 4 fields are there: source port, destination port, message length and checksum, and of course the data. So, in UDP the source port and destination port has usual meanings. Message length will specify the size of the datagram in bytes. Now, when you say datagram, this includes the UDP header plus the data. Checksum is computed in the same way as TCP. Same way means here also you include the pseudo header, you include all the fields of the IP which are relevant for computing it, and we use the same algorithm, that taking that one's complement and adding. But the point to note is that in UDP this checksum is not a mandatory field, you can also keep it optional. This field will be set to 0 if it is not used. Okay. Fine. Now, here let us try to just observe one thing. Now, we have two competing protocols at the transport layer level in the TCP/IP protocol suite. Just to recall, TCP provides you a connection oriented reliable service for the transport of messages. UDP provides you a connectionless unreliable datagram service. Now, if you try to find out what kind of applications would be using which of these, then very naturally you can say that, well, if you have an application which does not like to do any error checking out of its own, it wants the underlying network layer to provide all the reliability it requires, then TCP will be the choice for the application. But here there are a couple of things to note. See, a particular application, if it uses TCP, then it is true that you get very high reliability, you get a connection oriented service in the sense that before the data communication starts, you have to explicitly establish a connection. Okay? Fine. Now, but the price you are paying is that TCP is not a very efficient protocol. TCP is, you can say, a relatively high overhead protocol, it is relatively slow. But if you have some application where the size of the messages are not very large, they are small enough so that they can fit into a particular, say a particular packet, then you may choose to use datagram. But here the point to note is that the application should be such that if a few packets get lost in transit, because UDP will never give you a guarantee of correct packet delivery. So, the application should be such that even if there is an error in delivery, some packets are getting lost, either that loss can be tolerated or the higher level protocol must explicitly keep track of that. Okay. I am giving you two examples. There is one protocol, as I mentioned earlier, the trivial file transfer protocol TFTP, that uses UDP. Okay. But since the file transfer is a very important operation, even a small portion of a file, if it is not transmitted, you cannot tolerate that. So, TFTP exclusively keeps track of which of the portions of the file have been transmitted and which of the portions have not been transmitted correctly. Okay. But say you take another example, say for example, simple network management protocol. This SMTP is another protocol which is used to send some kind of network statistics information over the net, so that in a centralized location you can collect all the data and view the current health of the network statistically. in that application, well, even if one packet gets dropped, it does not matter, because the packet is sent every few minutes or so. Okay. So, it depends on the application. So, whether you really want to use TCP or UDP, fine. Now, the next question is, TCP and UDP are transport layer protocols, fine. Now, we are saying that application layer protocols or applications are which are sitting on top of it, they use either TCP or UDP. Now, as a programmer, I may ask the question that, well, how do I use TCP or UDP? Suppose I am writing a program in a language like C, C++, Visual Basic, anything. So, how do I really use TCP or UDP? Now, the answer is to have some kind of a standard interface. This is one very standard interface which people use. This is called Berkeley socket interface. Now, the name Berkeley socket interface, this has come because this interface was first, you can say, announced as part of the so called Berkeley socket distribution or BSD Unix. That was a very well known version of Unix which was developed at Berkeley, and this socket interface was developed as part of it. Okay. Now, this Berkeley socket interface is a means for accessing the TCP or IP services over the network. So, now let us see that how we can develop a network application. So, I am just giving you the outline, what is the procedure to be followed. Well, of course, some standard and well accepted protocols are the most desirable. So, in the modern day of computing, at the data link layer level, in most places you will find that the Ethernet protocol is in use. But of course, there are installations you can find somewhere where they use some other protocol like say FDDI or say ATM, some other protocol which is not Ethernet, but Ethernet is most common. At the level of the network, use IP. See, this IP is important because in today's internet, the whole internet infrastructure is sitting on top of IP. So, if it is not IP, then your packet cannot reach your intended destination where you want it to reach. So, it is mandatory to have this IP infrastructure in place if you want to be part of the internet. And with respect to the standard applications, at the transport layer level you can use TCP. Of course, UDP is another option, but most of the application use TCP because of the reliability it provides. At the application layer level, you use a standard application program interface like Berkeley socket interface. Now, in Berkeley socket interface, actually what happens is that here means you as a programmer, you are provided with a set of application calls, or you can say library functions. Now, using these library functions, you can do a host of things. For example, you are wanting to develop a connection oriented application. So, you will have to first establish a connection between the two ends. Now, for establishment of the connection, there are such system calls like socket, bind, accept and connect. So, whenever a client wants to establish a connection with a server, these are the function calls which have to be invoked at the two programs which are running on the two sides. So, at the end of it, the connection is established. Now when I say connection is established, it means that all the 5 components of that association that I told you about, the protocol, local IP address, local port number, remote IP address, remote port number. So, all these 5 things are known to both the ends of the communication. So, once this is so, they can start the communication, and whenever you open this kind of a connection, you have something called a socket. Now, a socket is very similar to a file in terms of its usage. Now, recall when you use a file, say in a C like program, first you have to open that file, you get a file descriptor, and using that file descriptor you can do read and write from the file. Now, here also a very similar thing happens. In the process of establishing a connection, something called a socket descriptor is returned. Now, using that socket descriptor, you can do a send or receive at the two ends. If the client makes a send, there must be a matching receive at the server end. Okay. So, this send and receive will go on as long as you need to do it, and at the end there will be another system call called shutdown or close for closing or terminating the connection. But for connection-less application development, for example, if you want to use UDP, there is no concept of a connection establishment, there is nothing called socket. So, there also you will be provided with certain system calls, but this system calls will be slightly different, send to or receive from. These are the names of the two system calls which are available. Now in these functions you need to specify all the 5 components of the association as the parameters. So, when you are sending a UDP packet to another process in another machine, you have to specify all 5 components of the association as parameters. Now, using those values you are passing as parameter, the UDP packet is constructed and is sent. Similarly, receive from will also get all the values from the other side, and those values you can read and you can find out from where the packet has actually come. So, using this Berkeley socket interface, you can develop any kind of network application which is running on a client server environment over the network, and if it is based on TCP and IP, which Berkeley socket is so this application can potentially run across any pair of hosts in the internet. For example, my client may be located here in my room, the server may be located in some, say means it may be located in US. Like when I browse the internet, I type in the name of a site. Now, the corresponding server may be located anywhere in the world, but sitting here I am able to access that. This is because this application was developed on top of TCP and IP. This is a standard which was maintained and followed. Now, we have talked about IP, we have talked about TCP, we have talked about UDP. Now, what we would be talking about in the next few lectures is that, well, understanding that today's network, today's internet is based on IP, we want to have a better understanding that exactly how these IP packets are routed and forwarded through the internet. Okay. So, this we shall be discussing in our next lecture. So, here we come to the end of this lecture number 5, but now let us have a quick look at the solutions to the questions which you posed on our earlier lecture. Okay. So, the first question was, an IP packet arrives at a router with the first 8 bits as 0100 0011, but the router discards the packet. Now, you try to understand what the first 8 bits in an IP packet mean. Recall that the first field in an IP packet is the IP version, the first 4 bits, and the next 4 bits will represent the header length. So, in this example the first 4 bits 0100, this will actually indicate the version, which is version 4, and that is correct. The last 4 bits 0011, this indicates a number 3. Okay. Now, 3 means this is the header length. So, the total header size will be 3 into 4 or 12 bytes, but this is an invalid number, because you know that a IP header must be minimum 20 bytes, which means that the second field, it cannot be 3, it must be at least 5 or more. Okay. So, due to this invalid value of the header length field, this IP packet will be discarded. Fine. Now, the next question. An IP packet arrives at a router, again with the first 8 bits are given, this combination. Now, the question is, how many bytes of option fields are there in the packet? Well, here again the first 4 bits will indicate the version, the next 4 bit will indicate the header length. Now, in this example the header length is 8. 8 means this will indicate 32 bytes of header, but the basic IP protocol requires 20 bytes in the header, and in this calculation we are getting 32. So, the difference between this 32 and 20, namely 12, this will be the number of bytes in the optional options field in the IP header. So, you calculate the actual number of bytes in the header, subtract the minimum value of 20, you will get the size of the options field, 12 bytes. Okay. In an IP packet, the value of the header length is 5 and the value of the total length field is 1000 in decimal. How many bytes of data the packet is carrying? Well, since the header length value is 5, this means the size of the header will be 20 bytes. Now, the total size of the IP packet is 1000 bytes. So, out of this 1000, 20 bytes are going for the header. So, the remaining 980 bytes will be the data. Okay. Fine. 4. A packet has arrived at the destination with the M flag bit as 0. What can you say about the packet? Well, now here you recall that the M bit in a packet is used for the purpose of fragmentation and assembly. It is a more fragment bit. If M is equal to 1, it means that this is not the last fragment of the original packet, there are more which follows. So, if the M bit is 0, which means that there are no more fragments following this. So, here there are two alternatives. If the packet was fragmented, then this is the last fragment because M is 0, but if the packet was not fragmented, if it is the original packet in itself, it will anyway have the M bit as 0. So, if the M bit is equal to 0, we cannot say whether the packet was fragmented or not. What we can say is that if the packet was fragmented, then this is the last piece of the fragment, okay? But we cannot say whether it was fragmented or not. Fine. Now, the next question says that the M bit is 1. So, here what can we say? Well, M equal to 1 means this is a fragment, because a normal packet can never have the M bit set to 1. M equal to 1 means there are more fragments following. So, the packet must have been fragmented and this is not the last of the fragments. These are the two things we can say. So, the packet has been definitely fragmented and this is not the last fragment. These are the two things we can say. Okay. So, a packet has arrived with the M bit as 1 and also the fragment offset field as 0. What can we say? Well, fragment offset field as 0 means this is the first fragment. M equal to 1 means that it has been fragmented definitely. So, we can say that there has been fragmentation and this is the first fragment. Okay. Next one, this says that the fragment offset field is 500, then what can we say? Well, fragment offset field is 500 means that you recall that fragment offset field is specified in multiples of 8 bytes. So, with respect to the original message, if this is the original message and suppose the present fragment occurs here in the original one, then this offset value will be 500 into 8 or 4000. So, the starting byte number of the fragment with respect to the original packet will be 4000. Okay. Fine. Now, a packet has arrived at the destination with the header length as 5, fragment offset 150 and the total length field as 2000, then what you can say? Well, since the fragment offset is 150, we can say that the first byte number is 150 into 8, 1200. The header length is 5 means 20 bytes of header. The total length is 2000. So, we can say 1980 so many data bytes are there. Now, since the first byte number is 1200, so the first byte in the packet corresponds to 1200, the last byte corresponds to 1200 plus 1979, which is 3179. So, with respect to the original packet, the present fragment's beginning byte position will be 1200, the last byte position will be 3179. Okay, this is what we can say. Change the following IP address from binary to dotted decimal. This is easy. You take each of these 8-bit chunks, convert them to decimal and write the number separated by dots. Find the error in the following IP address. Well, these decimal numbers correspond to 8-bit binary strings. Now, an 8-bit binary number can have a value, unsigned value from 0 to 255. Now, this IP address notation has a number 256, which is invalid. So, this is not a valid IP address. Find the class of the following IP address. Well, because it starts with 227, you can easily see it is a class D address. Given the network address 135.75.00, find the class, network ID and the range. Since it starts with 135, it is class B. The network ID for class B are the first 2 octets 135.75 and the range will be, for the host part we apply all combinations starting from all 0 up to all 1s. This is the range. Given the network address this, find the class, network ID, range, same. Now, 216 means class C. Now, for class C the first 3 octets will be the network ID and the range, the last one can be starting from all 0 up to all 1s. This is the range. What do the following IP address signify? Well, 144.16 means a class B address. 255 in the host part means it is a broadcast address. That means this address means you broadcast to all hosts on that particular class B network. This is a directed broadcast address. Well, an IP packet with 2500 bytes of data plus header passes through an IP network with MTU of 500. How many additional bytes will be delivered? Now, 2500 plus header will become 2520. Now, it passes through an IP network with MTU 500. You can easily see that a total of 6 fragments will get created. Now, each of these IP fragments will be carrying a 20 bytes of header. So, in the final destination 6 such IP packets will be delivered with a total of 120 bytes of header, but the original packet had only 20 bytes of header. So, 100 bytes of extra header information will be delivered. Okay, fine. So, now let us very quickly look at some of the questions from today's lecture. What does the port number in a TCP connection specify? Why it is necessary to have both IP address and port number in a packet? Which of the layers TCP, UDP and IP provides for reliable communication? Both UDP and IP transmit datagrams. In what ways they are different? What are well known port numbers? What are ephemeral port numbers? With respect to a transport level connection, what are the 5 components in association? This we have discussed. Why is this pseudo header used in calculating TCP checksum? What are the different fields in the pseudo header? Okay, fine. Well, here is a question on TCP. Suppose that 5000 bytes are transferred over TCP. The first byte is numbered 20,050. What are the sequence numbers for each segment if data is sent in 4 segments, with the first 2 segments carrying 1000 bytes and the last 2 segments carrying 1500 bytes of the data? Now, the first byte number is 20,050, means the numbering will start from that 20,050, 20,051, 20,052. This all these 5000 bytes that are being sent, they will be numbered accordingly. They will be split into 4 different TCP segments. So, in this question you will have to say that in these 4 segments how will be the byte numbering taking place from the starting address, the ending address. This you will have to find out. What is the purpose of the push flag in the TCP header? What is the purpose of the acknowledgement ACK flag in the TCP header? Well, if you are developing a network application on a reliable LAN environment, which of TCP or UDP would you prefer and why? So, these are the questions from today's lecture. So, as I mentioned, in our next lecture we shall be talking about something related to routing in IP networks, how the data packets actually flow through an IP network and finally finds their way to the ultimate destination. Thank you. Now, we shall be starting our discussion on IP addressing and routing. Now, if you recall what we have discussed in our last few lectures, we had looked at the TCP IP protocol suite, we had looked at the basic functionalities of the IP, TCP and the UDP protocols. Specifically, we had mentioned that the IP protocol is responsible for the delivery of packets from a source to a destination through a number of intermediate nodes which are typically routers. So, we shall today look at some more details about how this addressing at the level of IP is achieved. So, IP subnetting and addressing is the topic of our discussion today. So, we start with something called IP subnetting.